Penelope, a Horizon 2020 funded project, aimed to develop an end-to-end digital manufacturing solution for flexible and highly accurate production of large parts in novel, connected factories. Penelope solutions were implemented across 4 industry-driven pilot lines: oil and gas, bus and coach, aeronautics, and shipbuilding. This video presents the shipbuilding demonstration focused on the production of fitting pipes. This part of the pilot line was led by Fraunhofer IGP. Fraunhofer IGP in Rostock is advancing the future of shipbuilding through applied research and innovation. Focus areas include robotic welding, automated inspection, and digital production technologies tailored for maritime applications. Collaborations with shipyards aim to increase efficiency, reduce costs, and enhance quality across the entire shipbuilding process. By integrating intelligent systems and scalable solutions, Fraunhofer IGP supports the development of faster, smarter, and more sustainable shipbuilding practices. The achievements of this demonstrator in the Penelope project are the result of collaboration with key partners. Rena from Italy, Bieber from Germany, Ayman from Spain, ESI from Spain, DGH from Spain, Fraunhofer IGP from Germany, and TTPSC from Poland. Together, they contribute to advancing innovative solutions in modern shipbuilding manufacturing. The aim of this pilot line group was to improve the existing fitting pipe manufacturing processes. A fitting pipe is a prefabricated pipe section used to join or connect different parts of a piping system. An innovative process, developed as part of this project, will be demonstrated in the next steps. Scanning of the flanges on board and obtaining information about their whereabouts. Creating a route for the pipe between the scanned flanges. Creating paths for the robotic assembly. And using a robotic cell to perform assembly through human-robot collaboration. The result is a custom fitting pipe that precisely connects the initial flanges, completing the automated assembly process. Fraunhofer IGP has developed software that recognizes flanges and their orientation and position in a defined area from scanned images taken with a laser scanner. A laser scanner scans the entire area and produces a rough scan. The operator can then select an area of interest, i.e. the area containing the flanges. The scanning process is then repeated, but only for the selected area. The scanned images are transferred to a computer and then opened and processed by software. The software displays the image being processed. Operator clicks on the flanges to give the software an indication where to search for the flanges. Finally, the flanges are detected. The result is a document containing information about the relationship of the flanges and a point cloud of the environment, which can then be visualized in point cloud visualization software. The prototype Telegon, developed by Bieber, allows to transfer the measured start and end points of the fitting pipe into the CAD environment. For this data exchange automation ML standard is being used. The user can choose a knot in the AML tree and the CAD information is stored below. Telegon connects directly to the active assembly model of the pipe run. The Telegon interface to CAD is used to let the 3D points appear in the CAD model as start and end point for a fitting pipe. Transferred measure points include orientation. This orientation is represented by XYZ vectors. If automated pipe routing is active, the designer can now reposition the pipe elements to fit between the new start and end point. Start and end point for each pipe segment are stored in AML. Telegon can pick up the pipe run data from AML and calculate the targets for the robot handling. DGH's trajectory manager is shown controlling robot motion in a 3D environment, converting simulation paths into executable programs, and handling trajectory updates directly on the robot system. Fraunhofer IGP has developed a semi-automatic robotic cell in which an operator works together with a collaborative robot to assemble a fitting pipe. The UR cobot takes the first pipe element from the pipe drawer and brings it to the flange. The operator tack welds the two parts. The UR cobot prepares the next part. The QCA robot positions the flange according to the information obtained from the scan images. The UR brings the second pipe element to the other flange. The operator tack welds these two parts. This process is repeated until the last part is positioned and tack welded. The last part has to be repositioned by the operator to achieve the optimal position. Finally, the fitting pipe is assembled. In addition to the semi-automated robotic cell for the assembly of fitting pipes, this project also explored the potential of additive manufacturing for producing custom fitting pipes using the WAM process. A collaboration between IMAN and ESI led to the demonstration of manufacturing a fitting pipe using WAM. The process begins with designing a 3D model in SolidWorks, based on specific functional requirements and material properties, while ensuring compatibility with WAM constraints such as layer thickness and thermal expansion. Next, tool paths are generated for the robot-controlled welding torch, and the deposition strategy is optimized to minimize defects such as porosity and residual stresses. The simulation phase includes thermal and structural analyses to predict distortions and fine-tune process parameters. Material deposition is then validated, and potential manufacturing challenges are assessed. Finally, layer-by-layer deposition using WM is executed in a robotic cell, with precise control of key process parameters such as voltage, wire feed rate, and shielding gas. Post-processing is carried out to enhance dimensional accuracy and mechanical properties. RENA defined the requirements for the application of the developed solutions in production and ensured regulatory compliance based on its extensive shipbuilding experience. The technologies in the pilot line were developed in accordance with the standardization framework established earlier in the project. These results represent an important step towards more efficient and adaptable solutions for fitting pipe assembly. The approaches developed offer practical benefits for industrial applications and lay the foundations for future advances in automated and additive manufacturing processes.